So you have to subtract your 0.0732 from 1 to get the correct value of mole fraction of B at 0.1. So this will be now 0.9268. And correspondingly, your XBM will be affected because your B1 must change to 0.9268. So we will change this one. 0.9268, 0.9723. Okay. And then you have this is 83.2 divided by 18. That would be moles of B at 0.1. So this should be changed to 4.62. This will change. This will change. So you will have here a 4.62. If you're going to add that to 0.3640, invert it and you multiply it by 100, that should give you 820 here. So this is where the error is. So 20.06. I think this one is correct. So this will be now 20.06. Your 972.8 we divide by 20.06 and we add it to 988.1 divided by 18.777 and we divide it by 2. Your CAV should only be 50 as what is written in the book. So it should be only 50.56. 50.56. Then you go back here and change this to 50.56. So if we will now have it multiplied to the rest of the values we have in the equation, XA1 will change to 0.0732. Change it already. So we have an 8.97, comparable to what's found in your textbook. So this is 8.97 times 10 raised to negative 7 with the unit of kilomole per second per square meter. This is already the flux. This is the flux of A, or the rate in which your A, in this case ethanol, is going to diffuse to the solvent, or the organic solvent that is stated in the problem. So this is our first sample problem for this afternoon under liquids. Now I'll go back to the slide. And we have now applied the formula that you are seeing on your screen. And that is your sample problem number 6. Now, if the problem does not give you the diffusivity of your solute to a particular liquid, you need to determine that particular diffusivity by simply using this table, table 6.3-2, making use of the um, atomic and molar volumes at normal boiling point of the atoms present in your solute. So for dilute solutes in liquid, this is the formula in determining or predicting the diffusivity of a particular solute in a given solvent. So for smaller solute molar volumes, if the molar volume of your solute is very small, then it's considered to be dilute in the solvent. Then the formula that you are seeing here on top is reduced to this one. Now, everything that appears in the formula is defined in here, and where your MB is the molecular weight of solvent B, your U sub B is the viscosity of B in Pascal second or kilogram per meter second. Your V sub A in the formula, this one, also appearing on top, is the solute molar volume at the boiling point. And this can be obtained from the table that I have mentioned. And this phi is an association from parameter dependent on the particular solvent in which your given solute is going to diffuse to. So if your solvent is water, your phi is 2.6. If it's methanol, 1.9. For ethanol, 1.5. For benzene, 1. For ether, 1. For heptane, 1. And for other unassociated solvent, it's okay to assume that this phi is equal to 1. When when water is the solute but not the solvent, the value that you're getting from the particular formula that we have on top is to be multiplied by 1 divided by 2.3. That is, if water is not the solvent, but rather water is the solute. So the value that you're getting here will be, if it's dilute solutes in liquid, this will be the formula that you are going to use. But if water is the solute, you're going to multiply or divide your answer by 2.3. If you have a solute in very small molar volume, and that is your solute is diluted in the solvent, this will be your formula, and you are to divide your answer in the same way here by 2.3 if water is not your solvent but rather your solute. So in here, you're going to get the atomic volume of the atoms present in your particular solute A, as defined in here in this particular paragraph. You're going to take from table 6.3-2 the solute molar volume based on the atoms that are present on it. So we have here a sample problem that will allow us to determine the diffusion coefficient of acetone in water. So we are safe, water is not the solute here, but rather is the solvent in which your solute is mixed into. So this is an aqueous solution of acetone at 25 degrees Celsius and 50 degrees Celsius using the Melky-Wang equation. So the Melky-Wang equation is the one that I have shown to you here, this one. If it's the very dilute, we can use this one. So specifically, if you want the Melky-Wang equation to use, in this case, let me just check so that you will not get lost in here. This will be the one below. So since the problem is stating that you are to use the semi-empirical equation, the Melky-Wang, in predicting the diffusivity of, in our case here, of ethanol in water, then we are to use the said formula. Okay. So that one, this one is different. So that would be for biological solutes already. So we'll go back to our board. Okay, so we'll write down We'll start with, again, the formula that we can use and determine, work our way from the formula, work our way through the solution using the formula. For the Milky Wong equation, I will rewrite it here. So that's our equation in approximating the value of the diffusivity of ethanol in water. So we will check based on the problem. I read the problem, what we have and what we still don't have. So predict the diffusion coefficient of ethanol in water at 25 degrees Celsius and 50 degrees Celsius. So in this case, we need to determine this for temperatures of 25 degrees Celsius and 50 degrees Celsius at these two temperatures. The experimental value that is given, so I'll write here the experimental value, and let's say we'll compare that experimental value to the actual that we are solving. So it's 1.28 times 10 raised to negative 9. Right. 1.28 times 10 raised to negative 9 meters squared per second, and this is at 25 degrees Celsius. Okay. Now we will determine what we have in the formula already or what we still need to determine. Now, first in the formula that appears is the phi. And that phi is the association parameter of the solvent. So this is water that we're talking about. So this is already checked because we know that for water, our phi, I'll write it here, is 2, as read a while ago in the paragraph, it's 2.6. The next thing that we're going to look into is the M sub B. That's the molecular weight of the solvent B. Molecular weight of the solvent B. And that's for water. Our solvent is water, so this would be just 18. So again, we know this already. The temperature is stated. So in the first condition, it's 25 and the second is 50. So I might as well check this one. So our temperature is dependent on the scenario in which we want to determine the diffusivity. Then we have mu sub B. Mu sub B is the viscosity of your solvent, and that is your water. So this should be taken from a property table for water. So your mu sub B will be 2. You get it either from Appendix in John Couples or McCabe, if a McCabe has this, or more importantly, you use your handbook, so you get to use your handbook as early as now. So your mu sub B will be at two temperatures, at 25 and at 50 degrees Celsius. So since the book has already given us the mu sub B at 25 and at 50, I might as well use this one. So in your case, this will not be given to you. You will be the one who's going to look for this in the appropriate property table. So times 10 raised to negative 3 Pascal second. And at 50, this is 0.5494 times 10 raised to negative 3 Pascal second. So we're good with this. And the last is your V sub A, which we define as the, let me check, what is that V sub A? M sub B is the molecular weight of B, mu sub B is the viscosity of B, V sub A is the solute molar volume. So that's the one that we are going to get from the table. So this we will get from the table which I've shown to you a while ago, which is table 6.3-2. So I will put a note here to be taken from table 6.3-2. And we will go back to this particular table so you would know how to find the V sub B. So in the next sheet, we will just write the V sub B and how we're going to determine it. Just like our previous sample problem in the gas. So it's, I think, the same as this one. So I'll go to the slide and show to you what is this table. Okay, the table that we're referring to is this one. This is our table, table 6.3-2. In the first column, you have the atoms. In the second column are the corresponding atomic volumes of this atom, and it's times 10 raised to 3. So that means that the values that you will be able to get from this table or read out from this table should be multiplied to 10 times multiplied to 10 raised to -3, because the values that are shown here is already multiplied to 10 raised to 3. So in the case of our sample problem, we are given acetone. I will just pick the values here. Anyway, you know already how the table looks like, so I can go back to the board that we are using. So in the case of, I'll write here the formula for acetone. So your formula for acetone is CH3COOCH3. Only one. CH3COCH3. So this is for our acetone. This formula will guide you in determining the molar volume at the boiling point. So in this case, I will get from the table. Anyway, I have a copy of the table. So our acetone has 3 carbon atoms. So that would be 3 multiplied to the molar volume of carbon, which is 14.8. But in this case, it has to be divided by 1,000. So it could be now 0.0148 because the original is 14.8. So we divide it by 1,000. The next is for the oxygen. We have 1 oxygen, and it should be multiplied to the atomic volume of oxygen, which is 7.4. So this would be 0.0074. We need to divide it by 1,000. And next would be for the hydrogen, and we have 6 for hydrogen. Corresponding atomic volume is 3.7. So 0.0037. So we have now the VB in this case, which is 0.0740, and this has a unit of cubic meter kilogram mole. Cubic meter per kilogram mole. Okay, this is the, shall we say, the molar volume at the boiling point. So we now know the V sub B. We just go back to the formula and substitute. So everything, now you need to determine the DAB at 2 temperatures. So at 25 degrees Celsius, and that would be in Kelvin equivalent to 298. So 298, thank you, Dan. Kelvin. So you will have DAB this one, the DAB formula that we have. So 1.173 times 10 raised to negative 16. Our phi value is 2.6 for water. Then you have your MB, which is 18. And the two should be, the product of the two should be, wait, should it be the entire, okay, the product of the two, we will get the need to get the square root of. So we'll need to put this under the square root sign. Then we have the T. We have 298, and we divide it by mu B. So this would be our mu B, 0.8937. Negative 3. And we have something multiplied to this, the VB, which is to be raised to 0.6, and this is that value. So we need to multiply this with 0.0740, which is to be raised to 0.6. The entire thing will be the multiplier to this expression here on the left side. So you will have a DAB for 25. You do the same for the other temperature. The procedure would just be anyway similar. So let's say we'll check the value that we're getting times 18. We get the square root of that. We multiply to 1.173 times 10 raised to negative 16. And multiply it to 298. We divide it to 0.8937 times 10 raised to negative 3. And we divide it by 0.0740 raised to 0.6. Let me see. So your DAB value is 1.27. 1.276 times 10 raised to negative 9. This will have a unit of meter squared per second. The experimental value that is given is 1.28. So there, anyway, the predicted value compares to this. So 1.28, this one is more or less 1.28. I leave to you the other procedure for determining the DAB for at rather 50 degrees Celsius. Anyway, it's based on the formula. The key here is you know where to find what you will substitute to the formula. Because even if it's just a case of substitution, if you don't know what a particular parameter or variable represents and where to get it, then you won't be able to just simply substitute all the value to such formula. So there's a need for you to know the table where you need to get the value. And since I'm basing everything on Janku, please check the equivalent of this in your handbook because it's your handbook that you will be using again in the board exam. So I will go to the next topic on the slide. Okay, so we're here, we have predicted diffusivities. So in a problem, for example, in diffusion of liquids and even in diffusion of solids, if the problem will not give you this one, you should be able to determine it. And that's already applying or hitting two birds in one stone, because you get to apply this particular principle together with the particular principle of diffusion for, let's say, a gas or a, in this case, liquid, because we haven't yet discussed the solids. Now, this is the sample problem. Now, there's also a way of determining diffusivities for biological solutes. Biological solutes meaning they are made from like this, urea, or glycerol, glycine, all the things that you are seeing here. These are very limited because these are the things that are found only as a sample. I took it from, again, our book by John Kuplis. You may have even a more comprehensive equivalent table than this. So how do we determine the diffusivity of biological solutes? So we have the formula in here. So it's semi-empirical also in nature. So it's 9.40 times 10 raised to negative 15t divided by mu times the cube root of m sub a. Now, this formula is more generic, meaning it does not have any limitation. The formula that you are seeing in your book, if you're going to read on it on your spare time, it has a limitation, the original formula. So I chose the one which is not limiting. So this one is applicable for aqueous solutions, dilute aqueous solutions, wherein Ma is the molecular weight of a molecule of A, which is said to be large. Now, this is just one formula that Jean Pouplis shared to the reader. So if the, for example, if the shape of the solute is not spherical, because this one is limited to spherical molecules, then you can use this, but of course you expect that there will be deviation in the actual experimental value of that particular solute if it's predetermined prior to using the said diffusivity in the problem that will need it. But in this case, this is the one that is only shared to us by the author of the book. Now, in this formula, you will need the diffusivity in here. These are the only common. These are the only common biological solutes. So if the problem does not give you a solute that is in the table, you should be able to solve its diffusivity. That way you can solve whatever the problem requires. Of course, you need to also to know the molecular weight of such a biological solute. Now, what's the essence of having to know this or being able to predict diffusivities of biological solutes? Now, if you are a chemical engineer, your world is not only limited to physical processes that does not have any that has have nothing to do with anything that has to do with biology or anything that is living. For example, in fermentation, that's a biological system. So there are diffusion paths that happen in your, shall I say, in your fermentation system. And even in our own life processes, we also have diffusion of shall I say, very important solutes in our blood system. So you need also to study about diffusivities of this particular biological solids, some of which are already seen on the table. Sucrose is here, we have glycerol is here even. Okay, now we have a very short sample problem that will utilize the table that was shown to you in here. That way later on, if there's a need for you to know how to utilize the table, then you will know, of course, because you know the formula to use. Now you are in this table asked to predict the diffusivity of bovine serum albumin at 298 Kelvin in water as a dilute solution using the modified Poisson's equation. The modified Poisson's equation is the one that I have shown you. The other one I did not show anymore because it has, as I've said, a limitation. So this one doesn't have, except that your molecules, your solutes, have to have a shape that is spherical. Now, and compare it with the experimental value that is found in table 6.4-1. So if you go back to our table, there is this bovine serum albumin here, and its diffusivity is given to be 6.81 times 10 raised to negative 11. So what are we going to do? Sorry. So we will solve it. We will solve for the diffusivity of this bovine using the Poisson's equation and compare it with what we have in the table. Okay, so I will stop sharing here and go back to our slide again. If I will get disconnected, if I'm not sure if we can still use the same link, I will just make another link and share it with you. Okay, so we go to this. Our starting point here is the Poisson's modified semi-empirical equation. It's given by DAB being equal to 9.4 times 10 raised to negative 15t, and has to be divided by mu, and it has to be multiplied or divided by the cube root of the molecular weight of A. So the formula only needs the mu and the t, and of course the molecular weight, which we are going to get from the table. So we'll have a 9.4 times 10 raised to negative 15. The temperature in the problem is 298, 25 degrees Celsius. It's understood to be in Kelvin because that's absolute. The molecular weight is also taken from the table. So I've shown to you the table. I just place in here the molecular weight. So we need the cube root of that value, and that's 67,500 kilogram per kilogram mole. The viscosity that you're going to substitute here is the viscosity, of course, of the solvent. We don't have the viscosity of the solute. We're using the viscosity of the solvent at the indicated temperature. Again, if the problem does not give you the viscosity, you know where to find the viscosity of water. So your mu for water at 25 degrees Celsius is 0.8937 times 10 raised to negative 3. Okay, so you will have a DAB value equal to 7.70 times 10 raised to negative 11. This is meter squared per second. As expected, it will be really deviating from what's in the table because the table value is only 6.81. This one is far from that because this one is just, as I've said, it's semi-empirical, and it's already actually the modified version of the original formula. So this is just how we determine the diffusivity of a biological solute if its value is not found from any property table where we can read it directly from. Okay, now in 5 minutes I will be cut, so we will have a break, a 15-minute break, then we will continue. Just in time for me to make another link. So, for now, I'll go back to our slide. Okay, so that's it. Then next will be the sample problem that talks about diffusions in biological cells. So in here, you're given a tube or bridge of a gel solution. A tube or a bridge of gel solution which consists of 1.05 weight percent agar in water. So we have this agar in water at 278 Kelvin, very low temperature. So only around 5 degrees Celsius, which is, this particular tube is 0.04 meters long and connects the two agitated solution of urea in water. So we are expecting that this time urea is going to diffuse in our agar in water solution. So the urea concentration in the first solution is 0.2 gram mole urea per liter of solution. And of course, in the other side, it's 0. If we don't have this difference in concentration of our urea will not diffuse to the other side. We know that mass transfer will occur if there's a concentration gradient. So we expect also that this urea with this concentration will diffuse through the agar water solution to the other side because this agar water solution connects the two containers which are homogeneous using an agitator. You are to calculate the flux of urea So as I expected, urea is the one that is going to diffuse in this particular scenario. So in this case, what particular formula are we to use since we have urea diffusing to a different container that does not have any urea through this particular gel solution consisting of agar and water. So we will go back to a more general equation that we have learned before, and that's the diffusion between liquids. But in this case, we will have diffusion through a non-diffusing or a stagnant liquid, or shall we say media. Non-diffusing stagnant media. That non-diffusing stagnant media is our agar in water solution. So we will use that particular formula for diffusion in liquid. So we will go back to that particular formula in here. So that's the formula that we will use as a starting point. This one. We will use as a starting point in solving this particular problem. In this case, since we have a dilute solution, its XBM will be equal to 0, and the simplified version of the formula that you are seeing on top will be used. So this is the formula that we're going to use because our solution is dilute. So you may wonder, how do you check, Miss, or how do you tell that your solution is dilute? So let's go back to the problem and see why uh, are we simplifying it by using the simplified formula, and why is it dilute. You could see this particular concentration, a 0.2 gram mole. Take note, it's a gram mole urea per liter of solution. If you're going to convert this to kilogram mole per cubic meter, this value will be very, very small. So we say that even though we have a concentration gradient, but it's a dilute solution of urea in water. So in this case, we can simplify the solution to the problem by making use of that particular formula that I have shown to you. So we will be using this formula here for diffusion of A, and that's our urea, through a non-diffusing B. B will not diffuse to urea, but urea is free to use B as the medium so that it can transfer through the other chamber containing a solution, or the other chamber that does not actually contain any urea because its concentration is 0 in urea. In that particular problem, the medium for transfer is your biological system consisting of agar and water. So we will be using this particular formula. So we'll start with the formula.